Okay, so today I am teaching about resistance, resistors, and conductance. This topic, there are a lot of ways. This is a very general topic. There are a lot of different problems, a lot of different things you can do to cover this topic. It's very broad, and I'm going to give you a taste of it. Hopefully, I can give you some of the most important parts, but yeah, I got four different ways of, or four different equations and not necessarily equations, but four different problems that cover this topic here for you. So we'll jump right in. The first one right here, all four of these I want to find the resistance. And so the first one says find the resistance of a resistor with color bands brown, red, green, gold. And I'm sorry, I don't have a brown and I don't have a gold. So you're just going to pretend that you're just going to read the words and not look at the colors. But we've seen these in lab. So it's a resistor. It's just a little wire with a little doodah in between the wires, and there's a color. There's four colors on it, and they each represent a different thing. The colors correlate to numbers, and the order of the colors determines the resistance of the resistor. It doesn't necessarily determine it, but it tells the person who owns the resistor how much resistance is caused by that resistor. And so the brown is 1, the red is 2, the green is 6, I believe, the green is 5, and the gold is 5% tolerance. Okay? And so the first color here is going to represent the first digit, okay, to our number, to the resistance. Okay? The second number represents the second digit to our number. Okay, so we have 12 so far. The third number represents the number of decimal places, right? The number of tens, okay, scientific notation. That's this number right here. Number of tens we multiply by the decimal places. And the fourth color is the tolerance, which is the definition is possible percentage variation of resistance about the normal value. And so really what it is in English, it's the amount, give or take, the amount of error. This isn't an exact number. It's not exactly 120,000, or is that 1.2 million? Yeah, that's 1.2 million. It's not exactly this number, okay? It's got a tolerance. It's got a plus or a minus. And so the plus or minus is 5%. So plus or minus 0.05 times the number we have. And so this is how many ohms a resistor with that color shade would have. And there's these numbers I got. There's a big table out there with the correlations, and so it's in our book. You can probably find it anywhere on the internet, but yeah, that's how I got those numbers, and that's what they correlate to. And so for the second one, an element with a conductance of 0.05 Siemens. And so we're going to use this equation right here for number 2. Resistance equals 1 over the conductance. This one's pretty straightforward. I'm kind of going to zoom through it. The resistance is 1 over 0.05. Okay, which equals 20, I believe. Yes. 20 ohms. And so conductance and resistance is just inverse. They're both inverse of each other. So the third one, find a resistance of an aluminum bar, 7 meters in length and 0.4 centimeters by 2 centimeters in rectangular cross section at 20 degrees Celsius, which is just room temperature. And so for number 3, we're going to use this equation right here. I'm going to copy it over here. Resistance equals rho length times length over area. And so rho refers to a constant that deals with the material of the bar and the temperature of the environment the bar is in. And so at 20 degrees Fahrenheit, aluminum's constant is, let's see here, 2.83 times 10 to the negative 8. 2.83 times 10 to the negative 8. Okay, the length is right here. Length is 7. And the area, should I convert that to, okay. The area is, okay, so the area, right, the area is going to equal the length times the width of the cross section. So 0.4 times 2, right, those two numbers multiplied together, except it's centimeters. Okay, so we got to add that 10 to the negative third in for both of them to account for the centa in centimeters. And so when you do that math, the resistance is going to equal out to 0.248 ohms, roughly. And for the fourth one, find the resistance of a branch connected in series to a 7-volt battery drawing 7 milliamps. 27. I'm going to put 27. That's what I meant to put. Sorry about that. 27 milliamps. Okay, so what we have here is a circuit with a branch. Right, we're looking for the resistance in that branch. Okay, it's connected to a battery and it has a current, right, of 27 milliamps. This is 7 volts, and we don't know how much resistance is in there. Okay, and so I guess although the direction of this arrow isn't important to this topic, I believe that it goes in that direction because of this battery. But either way, the current is same throughout the entire thing, no matter what direction it's going, because it's just a square. It's a very simple circuit. But for number 4, we're going to use this equation, which is derived from your favorite equation, V equals IR. So the resistance is going to be equivalent to the voltage over the current. Okay, and our voltage is 7 volts, and our current is 27 milliamps. 27 times 10 to the negative third. Right, because we need to account for this milli right here. That's the 10 to the negative third. And so when you do that math, 7 over 27 times 10 to the negative third, it's 259 kilo ohms. 259 kilo ohms. Okay, so in 4 different ways we found the resistance in different scenarios, and we went over resistance, resistors, and conductance in 4 different problems. So that's all.